If you and I weren't Mu Alpha Theta members, and I told you that math could benefit agriculture, you'd think I was joking. But today, a specific type of agriculture, precision agriculture that is, using mathematics and technology to maximize efficiency is on the rise. And I'm here today to show you, like in so many other areas, that math is fundamentally revolutionizing precision agriculture as we know it. Before we talk about the solutions, let's address some issues. We are really privileged to be well fed with nutritious food, but that cannot be said for everyone. Hunger affects 10% of the world, and that number is not expected to drop anytime soon. The world produces much more than enough to share, but it isn't making its way to people who actually need it. And of the food that we do have, more is wasted due to unsatisfactory appearance, quality, along with a lot of other factors. So what does that mean for us? We are the ones who drive change. We can use our quantitative skills to solve the issues of production volume, of controlling disease, of manipulating the market, and so much more. So let me show you how it is done. So let's begin with the statistics, which is the best for determining the ideal methods of growing. So what are some factors to consider? We can start with hypothesis testing with simple variables to solve common questions, such as, do specific fertilizers, or soil types, or lighting types, or even irrigation produce significantly higher volumes or masses of food? Let's perform a significance test on two types of fertilizers. Say we're growing corn, which is one of the most versatile and widespread crops. We have two brands, Old Farmer's Almanac and Dr. Earth, and we'll be conducting a two-tailed t-test for a difference in means. So under similar conditions, such as the fertilizer amount, temperature, sunlight, we sample 50 randomly selected ears of corn from each treatment. And we find that Old Farmer's Almanac produces ears of corn with mean weight 1.3 pounds and standard deviation 0.1 pounds, while Dr. Earth produces ears of corn with mean weight 1.2 pounds and standard deviation 0.2 pounds. So all of our conditions are met. Our corn is randomly selected from each plant treatment. There are more than 500 ears grown on the corn of each plant treatment, and our size of sample of 50 satisfies large counts. So our test statistic is as follows. It's the difference in means. We'll say that mean 1 is Old Farmer's Almanac and mean 2 is Dr. Earth. So we have mean 1 minus mean 2 over the square root of the sum of the variance squared, or the standard deviation squared, over the sample size. So we have u1 minus u2 over the square root of sigma 1 squared over n plus s2 squared over n. So that's what we have so far. We plug in the numbers. 1.3 minus 1.2 over the square root of 0.1 squared over 50 plus 0.2 squared. And that gives us a test statistic of 3.16228. And on our distribution, that looks like this. The data is mostly on the tails. And if we run a CDF test on our calculators, we can find that the probability of this happening is very, very small. The p-value two-sided is 0.00269. So under any significance level, really, most of the time we test under 0.05. But in this case, it's much lower than that. So we have convincing evidence that Old Farmer's Almanac produces a higher unit yield than Dr. Earth. And these types of hypotheses tests can be used for a very wide array of experiments. In the field of agriculture, calculus remains one of our best friends when coupled with statistics. Optimization is our key here. Once we have our best production strategies with our statistical analysis, we can then optimize. Many crops and animals exhibit what we call density-dependent growth factors. For example, as the number of cows in a pen increases, the average number of calves' birth decreases because there's less of a need for them to produce more babies to sustain themselves. So as farmers, we can manipulate the breeding process to maximize our yield because we don't care about the nature of the breeding patterns. So we can use a model such as the logistic growth model, and this explicit formula doesn't say much in the form. So our explicit formula is that the population y equals L over 1 plus BE to the negative KT, where B and K are arbitrary variables. L is our carrying capacity, that's our cap, and T is obviously our X, which is our time. So that's the explicit formula. But the calculus formula tells a very different picture, and that's that the growth rate dy dt is proportional to the population, which is constant times y, ky, but also it takes into account that our growth rate slows down as we approach that carrying capacity. So that's why we include the 1 minus y over L factor at the end. And so if we differentiate this again, we can see when is our growth rate maximized, and that's what farmers want. They want the fastest breeding time for animals. And so that, if we differentiate, let's expand it out first. Ky minus ky squared over L dy dt equals. And now we differentiate with respect to y, so we have k minus 2ky over L equals 0. So this gives us that y equals L over 2. And so that means that when our population is at exactly half of carrying capacity, our animals, crops, whatever it is that is density dependent, will grow the fastest, and that's where we should keep the population at to maximize our yields. So we've talked a lot about production of goods, but none of it could be possible without proper planning or distribution tactics. So for major companies, seemingly insignificant questions of transport and distribution become really realistic issues, and this is where game theory and graph theory can come into play. Let's say our 4 vendors are connected as such. We have 4 vendors with outgoing and ingoing arrows. The vendor with the highest rank will be able to most efficiently distribute their goods, so they want to distribute to vendors that have the most outward pointing arrows. So we'll start off by giving each node a score of 1 over n. In this case we have 4 nodes, so it will be 1 over 4. And then we repeat iterations by adding to their score the outgoing page rank of each of the connected nodes divided by the number of total paths going to that node, because basically we just want to reduce the significance of one connection, because multiple suppliers reduces the significance of each one. So our graph looks like this, and then let's calculate. So one's page rank will be like, so we have the page rank of 2. It's based on the page rank of 2. Page rank of 2 also starts at 1/4, but how many nodes are going into 2? We have 1 from 1 and 1 from 3. So we divide that by 2, and 1 also goes to 3, but 3 has 2 ingoing nodes in total, so its score is like that. And then that's for 1, and 2, let's do the same thing. So 2 has 1 outgoing node to 4, and 4 only has 1 node going into it, so, 1 edge going into it, so that gives us 1/4 divided by 1. And that's the only outgoing node that 2 has, so its score is also 1/4. And then we repeat, and so this is what it looks like throughout the second iteration. 3 has the highest reverse page rank score in this scenario. And then you just, because the scores should sum up to 1 within each column, we can have convergence. And then once these values converge with the help of a computer, of course, we can determine which vendor is the most successful in supplying across your products across the board. So through these examples, we can see that math can be utilized in countless areas that otherwise would be unknown to me and unknown to you. So we can see that the value of math is everywhere, and agriculture is just one place where we can put it to good use. Thank you.